This is section 15.3, partial derivatives. Partial derivatives take over the whole class. They're all over everything from now on. It's kind of like when the derivative was introduced in Calculus 1, where there were derivatives everywhere forever. Partial derivatives are going to be all over this class from now on. The objectives today are to get the graphical meaning of a partial derivative with respect to x or y, compute and interpret partial derivatives, and then we'll also get into second partial derivatives, and some of these are called something called mixed partial derivatives. As far as the data types we're working with, we're still stuck with functions of two variables mostly. We'll be thinking of a function usually as having two inputs, an x and a y, and we think of that as like a point in the xy plane, and then the output of the function is one number. It's the z, it's how high something is. So your function represents a surface. That's what we're mostly dealing with. So let's look back on what derivatives did in Calculus 1, and then we'll try to generalize it up to what partial derivatives are. So in Calculus 1, we had a function that had an input of one number and an output of one number. It was a function of one variable. And the derivative's meaning was, well, if you picked a point, C, then you could talk about the derivative at x equals c, and what it meant was it was the slope of the curve at x equals c. To get a definition that worked, what we would do is we would say, well, I want to take a slope, so I'm going to do like I want f prime of x to be called the derivative. I'm going to want the derivative to be a slope, so I'll set up a slope formula, which is like rise over run. I need the difference of two y's on top and the difference of the x's in the denominator. The two y's we'll use will be x plus a little bit and x. So I'll call the little bit h. And then in the denominator I need the difference of the x's, which is x plus h minus x, that's h. Now I want this little bit to be really, really small, so we say, well, I can't really plug in 0 for h because then I'll get 0 over 0, so instead we invented limits and came up with this whole plan of letting h go to 0. The notation was, well, we had like f prime of x or dy dx, or like you could write df dx for the derivative of the function with respect to x. The main thing that you need to pick out of this as far as notation goes is that this part means the derivative of. And it also has kind of in parentheses at the end with respect to x. So dy dx, the d dx part says the derivative of with respect to x. So dy dx means the derivative of y with respect to x. df dx means the derivative of f with respect to x. So that's what it meant in Calculus 1. Let's extend that. Now we have functions of two variables, which is this data type up above me. Let me get what I meant to put in these boxes. So now you're going to have a surface up here. I don't know, and you should imagine it as like a fluttering sheet up here maybe. And the function is, well, given any point in the xy plane, you plug x and y into the function and it gives you an output, and that output is how high up the surface is at that point. Let's do a little bit better. Okay, now we want to still be able to talk about the slope of this surface, and it's a little bit tricky because I can't use the old definition because it only had one input for variables. So what we'll say is we want the partial derivative still. Not still. Instead of saying the derivative, we will have to take the partial derivative of the function. When we do a partial derivative, we have to pick whether we're doing a partial derivative with respect to x or a partial derivative with respect to y. So you could do the partial derivative with respect to y instead if you wanted to. We still want it to be the slope, because I want to use basically all the same ideas that we had in Calculus 1, but now it's going to be the slope of the surface. Okay, this is where it gets very dicey, because the slope of a surface is actually really hard to, like, it's a tricky concept. So I brought a cylinder here that hopefully I'll be able to draw on. If I pick a point on this cylinder, the question is, what's the slope at that point? So let's say I go up, it's like sitting on its, we'll say it's oriented this way, where it's sitting kind of like the long way. If I pick a point on top of the surface, can you see that point? I guess maybe I'll make it a star. If I pick a point on top of the cylinder, it seems clear that the slope should be 0, because, well, kind of like no matter how you look at it, this is the top of the cylinder. There's no slope here. We're like up at the top of a mountain or something. At the top of a smooth mountain, the slope is 0. So at this point, it seems clear that we want whatever the derivative to be, we want the derivative to come out to 0. The tricky part comes when you pick a point that's not up at the top. Let's do like I don't know, I'll make a sun. So at this point on the cylinder, you should ask yourself, well, what's the slope? And the answer is, well, it depends what you mean. It seems like, well, yeah, obviously there's a slope here. The slope can't be 0 because, like, it's slanted this way. If you walk along this path, the surface is sloped. So we might say, like, okay, well, since it's going this way, we'll say that the slope is positive. But the problem is that, like, well, sure, if you go this way through the point, you see this? This is not very high tech. If you go this way through the point, then you're walking uphill. And so we should say that the slope is positive. But if you walk a different direction, if you walk that direction along the surface, the slope is 0. So the critical thing is that the slope at a point depends on what direction you're thinking of. In this direction, if I go like left to right the way I have it oriented now, the slope at this sun point is positive. But in the other direction, the direction toward you, the slope is 0. So I have to pick which direction I'm looking, and those are called the partial derivatives. There's 2 different partial derivatives of a surface. One of them is with respect to x, and one of them is with respect to y. And they'll come out to different numbers. That's because, like, surfaces are either sloped or not, depending on the perspective you have. So we're going to say that we're getting the slope of the surface at a point. So I'll have this like base point, x0, y0. But if I'm doing a partial derivative with respect to x, what that means is I like walk parallel to the x-axis. I like walk in the x direction and see what the slope of the surface is. So like in the x direction. If you pick a different direction, if you instead walk parallel to the y-axis, you might get a different slope. So on this picture that we have in the notes, you would follow this curve, because this curve heads in the x direction. And you'd say, okay, now I have a curve, and I want to know at this point, what is the slope? And it looks like, for my weird picture, maybe the slope is like slightly angled down. So I might get a slight negative answer for the x partial derivative. Okay, so what's the definition? In order to get this picture to line up, with a definition, what we do is we say, well, if you're doing the x partial derivative, you stay on the surface at a fixed value of y. So partial derivative with respect to x. We do the exact same thing that we did in Calculus 1, which is we set up a slope. But now we have 2 inputs, and the question is like, well, what do we put in there? And the answer is we say, well, for the x partial derivative, we want to let x change. We're like we're changing our x coordinate, but we're going to keep y the same. So you kind of like do the derivative, but you say, no, x is the only variable we're allowing to change. Y is just going to stay constant. We'll always plug in the exact same y. On the picture I have here, that's this y value, y0. If you want to do the partial derivative with respect to y, you do the same thing, but you fix x and you let y change. So this will be f of x y plus h minus f of x y, and divide all that by h. Let h go to 0. So these will be our, this is the x partial derivative of f, and this is the y partial derivative of f. Okay, we're going to need some notation for this, because these aren't regular old derivatives. They're like weird derivatives where we're not really letting the function do its thing. We're fixing some things and varying others. The notation that tells you that you're fixing some things and varying others is you use this d instead of the normal d that you use for derivatives. So this thing here is indicates a partial derivative with respect to x, and it's read as partial x. Which is really strange. So you don't say this as d, because if you say d, then you're talking about this thing. This is d dx. So like you would say dy dx for the derivative of y. You would say partial y partial x for the partial derivative of y with respect to x. So the notation we'll end up with is something like, you'll write partial f partial x if you want to take the derivative of a function, fixing all the variables except x, letting x move around. Or you might do the y partial derivative, and you'll do partial f partial y. Now, as you remember from Calc 1, we need lots of different modes of this. Another way to write this is to say, well, I want f, and I want the x derivative of it. You just write the x as a subscript. So this f sub x means the same thing as partial f partial x. It means this definition, and it means that thing that we had in the picture, where we're walking on the surface and we're just walking in the x direction. I think the only other maybe slightly longer way to write it would be to write something like this, to be clear about what's going on with the function. This is partial x of f of xy. And here's partial y of f of xy. Later, we'll have more complicated objects. Oops, I'm having trouble pointing. We'll have more complicated objects like functions of 3 variables, and the definitions will all just work exactly the same way. If you go far enough in physics, you'll get functions of 4 variables, and you'll say, whatever, it doesn't matter, it's fine with me. To take the partial derivative with respect to a variable, you just move in that direction and see what changes with your function. Okay, on to the next page. Okay, let's see some examples. I didn't really tell you how to use this, or how to do this actually. But the key thing is that if you're taking the x partial derivative of a function, then this gives you license to say that y is a constant while you're doing this calculation. So when we're taking the derivative of 3x squared y, I just keep the 3 because the 3 is a constant. But the strange thing is we also just keep the y because the y is a constant in this perspective, where x is the only thing that's varying. X squared, its derivative is 2x. Then we go to the next term. 6 is a constant. X is not a constant, its derivative is 1. Y squared is a constant. You need to practice a lot of these. That's why the homework problems, there's a lot of them listed. They're very easy once you wrap your head around what you're doing here, which is partial f partial x, which is the partial derivative with respect to x, is take the derivative, but treat x like it's the only variable and that nothing else is a variable. So derivative of x cubed is 3x squared. Derivative of y cubed, 0. Because y is a constant. In this situation, the only variable is x. So our final answer will be like 6xy minus 6y squared plus 3x squared. Then we can find partial f partial y. Same process. We just change our perspective to say now y is the variable and x is a constant everywhere that it appears. So 3, that's a constant. X squared, that's a constant this time. Derivative of y is 1. 6, that's a constant. X is a constant. Derivative of y squared is 2y. X cubed is a constant, so its derivative is 0. Y cubed, oh, the derivative of y cubed is 3y squared. Notice how the only difference, like we're still using the same power rule and we'll use all the other derivative rules that we've used forever, but the difference is which one is a constant and which one is changing. So my answer here is 3x squared minus 12xy plus 3y squared. A critical thing to note here is that if someone hands you a function of two variables, they can't ask you for the derivative of it. If they ask you for the derivative, you have to say, what do you mean, which derivative? And that's because of this idea that, like, given a point on a surface, you can't really tell me what the slope is until I tell you which direction you're supposed to walk. I don't know, I mean, have you gone hiking recently? Like, if you're walking on a slope, there's usually a direction you can walk that it's flat. But we don't want to say that every mountain is flat just because there's like a way to walk that stays at the same height. So instead, when someone asks you for a slope, when someone asks you for a partial derivative, they have to say which direction that they want you to walk. And then you can take the derivative. Okay, let's do this one. So we have z equals x sine y minus y cosine x plus e to the 5x. Okay, this is some surface. It's probably wavy. I don't know what it looks like. It doesn't matter. To take its partial derivative, we say, okay, the x partial derivative, we will now think of y as a constant everywhere. So this is x times a constant. So its derivative is the constant. Here's a constant times cosine x. Well, the derivative of cosine x is minus sine x, and we'll just keep the constant around y. The derivative of e to the 5x with the chain rule is 5e to the 5x. Now when we take the y partial derivative, we're thinking of x as a constant. So now I have a constant times sine y. The derivative of a constant times sine y is that constant times cosine y. It completely changes the derivative when you change your perspective, what you're taking the derivative with respect to. Cosine x, that's a constant, times y. The derivative of y is 1. And then here's e to the 5x, that's a constant. Its derivative is 0. So once you get used to it, it'll be fine. Okay, let's look at this one. It says that we're looking at the function z equals 3x plus 5y. That's a plane, so there's some like plane in space. I could ask you, what's the slope of the plane? And you would say like, I don't know, I mean, if you walk up the steep way, it's really steep. And if you pick the wrong direction, it won't be steep at all. So what do you want from me? What's the slope? Well, this is asking a more specific question than that. This says, walk in the x direction. What's the slope? Okay, well, partial z partial x is the derivative of 3x is 3, and the derivative of a constant is 0. So partial z partial x is 3. This means that on this plane, if you walk in the x direction, you go up by 3 for every 1 you go over. When you instead take partial z partial y, well, the derivative of 3x is 0, and the derivative of 6y is 6, so you get 6. This says that if you walk in the y direction, it's twice as steep. So this is a plane. Walking in the y direction, will be very hard because it's super steep. It's got a slope of 6. Walking in the x direction gives a slope of 3. A small thing you should check on yourself right now is to make sure you're not using d here. If you write dz dx, that's something totally different. That's like, and in this particular circumstance, that's just not a good idea to write that because we don't yet really have a good way to write down what that means. If you're declaring one of the variables to be a constant during your calculation, you're talking about partial derivatives, so you should use this partial sign, which is curvy d. This question brings up a question that would lead us into 15.5, which is 2 sections from now. The question that I would want to ask myself is, okay, if I've got this plane, do I have a plane handy? Like this. If I have a plane and it's oriented in space somehow and I'm standing somewhere, well, this tells me that walking one way walks up, and walking the other way walks up also. Well, there's other ways that would make me walk down. And it seems like there's always a way you could walk that would go horizontal. So like, how do we find those directions? Like, what about the other directions instead of just the x direction and the y direction? And that all gets settled in section 15.5. It's a really cool section. The idea of the gradient comes up, and it's pretty powerful. Okay, onto the third page. So now we want to find the slopes of tangent lines in the positive x and y directions at this point for this function. Okay, so this is I mean, I was about to say that this is the top half of a sphere. The reason it's the top half is because this is positive, a positive square root. If it was minus square root, it would be the bottom half. Number minus x squared minus y squared gives me a sphere. But then the x's and y's are scaled differently. So instead of this being the top half of a sphere, this is actually the top half of a stretched out sphere. It's called an ellipsoid. This question asks for some slopes in different directions. Those are the partial derivatives. So the first question is asking you for partial h, partial x. And the second question is asking for partial h, partial y at 0, 3. So let's do this. To take the derivative of something to the 1/2 power, you can do the power rule. And then since the inside is not a constant, you need to multiply by the derivative of the inside function. Well, the derivative of this inside function is, well, the derivative of 1 is 0. The derivative of y squared over 25 is 0 because of our perspective that x is the variable. So the derivative of the inside function is minus 1/2 x squared. So in total, I have x squared in the numerator. In the denominator, I have a 4 from the 2 times 2, and then there's a big square root down here. Okay, here's a good trick for like not having to write things over and over. I was about to write the square root of 1 minus x squared over 4 minus y squared over 25, but that already has a name in this question. Like, I was about to write this down again, and I don't want to do that. If something's already named, then just use the name of it. That's fine. So here's partial h, partial x. That's the slope of the tangent line in the x direction. Now, hang on. It actually says we want the derivative at 0, 3. So I don't know if you're familiar with the notation for how to plug something into the derivative, but you use a big vertical bar, and you put what you're plugging in here. And then you just drop 0 and 3 into the answer. So we'll get 0 squared over 4h of 0, 3. H of 0, 3, it's not 0, so we're going to have 0 over some number, so this comes out to 0. Okay, then let's do the second part. To do the second part, we'll get partial h, partial y. Same deal. it's a 1/2 power. So I'll use the power rule on the 1/2 power. And then I need to multiply by the derivative of the inside function, which has changed because we've changed our perspective from x being the variable to y being the variable. So now the derivative of the inside function is minus 2y over 25. 2's cancel. I end up with minus y. Uh-oh. Looks like I made a mistake up there. I dropped this minus sign. Okay, minus y over 25h of xy. Now the question wants the slope at the point 0, 3. So I'll find the partial derivative of h with respect to y at 0, 3 by plugging in 0 for x and 3 for y. Well, what is h of 0, 3? I need to plug it in to see. One minus 0 minus 9/25. Okay, 1 minus 9/25 is 16/25. The square root of 16/25 is 4/5. Can cancel out this a little bit. And I get minus 3/20. So partial h, partial x at the point 0, 3 is 0. That means walking in the x direction, this ellipsoid was flat. But then walking in the y direction, it was slanted downward a little bit. And that makes sense. On a surface, usually the slope is different depending on which direction you're headed on that surface. Challenge, use Maple. We don't have access to computer labs that have Maple this semester, so I don't think there's going to be... I could at least get a picture of it up from GeoGebra so you can... So remember, I'm going to geogebra.org/3D, which is our favorite 3D grapher. Square root. Can I get inside the square root? 1 minus x squared over 4 minus y squared over 25. So here's the top half of an ellipsoid. If we go look at the point, which was 0, 3, 4/5. 4/5 was h of 0, 3 that we calculated at the end there. You can see this, there's a point on the surface. If you walk in the x direction, it's flat. We're like at the top of the ellipsoid if you're thinking in the x direction. I wonder if I can get that to show up. I should be able to get that by just fixing y equals 3. Y equals 3, so 9/25. It's hard to see there. I want to just look at y equals 3, but I'm not sure how to restrict a domain in GeoGebra. Let's cut here while I Google this. Okay, we're back here after my trip through Google to figure out that I can restrict to just y equals 3. If the y coordinate is fixed at 3, so we're just walking in the x direction, then we're following this weird like tube along the top of the ellipsoid. And when we're at this point, 0, 3, 4/5, indeed the ellipsoid looks like it's flat. If we instead look at the, if we instead walk in the y direction, so let's fix that. We're fixing x equals 0. make it a little bit bigger so we can actually see it. I don't know, orange. I didn't get orange. If we instead follow this path, when we're walking in the y direction, we're going downhill a little bit when we reach this point, 0, 3, 4/5. So the x partial derivative is 0 because walking in the x direction, this is the top of the mountain. The y partial derivative is negative because walking in the y direction, this is a slight downhill slope. Cool. Okay, let's finish up these notes. So say you instead had a function that had more inputs. I'll turn on my little arrow here. Say you had 3 inputs. This wouldn't be a surface anymore. Instead of having like an x and a y input and the height is the output, instead the input is a point in space. Like say, here's an xyz that's right next to my head, and then there's a different xyz that's on my head. An example of a function like this would be like the temperature of a room. The temperature of a room in different places is different. Like close to a person or a light bulb or a computer, the temperature is higher, and further away from those things, the temperature is lower. So you plug in a point, xyz, and you get out a temperature. Well, what would partial, say w here is the temperature, partial w, partial x measures, well, if you walk one direction in the room, how is the temperature changing? Partial w, partial y would say, well, what about this direction? And partial w, partial z would say, what if I'm going up and down? How does the temperature change? The way you would calculate it in practice is don't worry about it. Like to find partial w, partial z is found by fixing x and y as constants. So when you're finding a partial derivative, you look at what variable you're taking the derivative with respect to, and you set all the others to be constants. So let's find some partial derivatives of this function. It's a function of 3 variables. To find the partial derivative with respect to x, we say x is a variable, everything else is a constant. So the derivative of x sine y, sine y. The derivative of y cosine x, well, this is a constant times cosine x. So I get minus y sine x. Here's a constant times secant x. So I need the derivative of secant x. And at the end here, I've got a bunch of constants. Don't care. Their derivative is 0. Partial f partial y. Okay, now I've got a constant times sine y. So the derivative is that same constant times cosine y. Here I've got a constant times y. So the derivative is the constant. Here I've got a bunch of crap with no y's in it. So the derivative is 0. And over here I have a constant times y. So the derivative is the constant. It might seem a little strange to do so many examples of this, but like we need to do this until you're annoyed that like you want to be thinking, oh my gosh, yes, I get it, please stop, because partial derivatives are extremely important for the rest of the class. So the z partial derivative of the first term is 0. The second term, no z's, doesn't depend on z, derivative is 0. Here's a constant times z, so the derivative is the constant. And then here's a constant times tangent z, so the derivative is that constant times the derivative of tangent z. So there's our 3 partial derivatives. I think we're going to do some second derivatives here in a minute. Let's see if I'm right. Yeah. Okay, so the second derivative for a regular old single variable function was, well, the second derivative was the derivative of the derivative. So it's how is the slope changing? So here I've got like a slope of 1, and here I've got a slope of a half. The slope is decreasing, so the second derivative is negative. So the second derivative for a single variable function told you which direction the graph was curving. If it was curving, like if it was concave like this, then you got a negative second derivative. If instead, like here I've got a slope of -1, and here I've got a slope of -0.5. The slope is increasing. If the first derivative is increasing, then the second derivative is positive. So we said that a function that was convex, like this, has a positive second derivative. So what can we do with second derivatives, with partial derivatives? Well, because there's like, let's go back to just thinking about surfaces where there's only x and y as inputs. You can take the x partial derivative to say what's the slope in the x direction. You can take the y partial derivative to say what's the slope in the y direction. The second derivative, you could do like, how is the x slope changing as you move in the y direction? Or how is the x slope changing as you move in the x direction? There's like a ton of options. So what are we doing for the function h of xy on the previous page? Basically, we're going to take the x partial derivative, and then you can take either kind of partial derivative of the x partial derivative. So you get tons of options of different second derivatives, even more than you had options of first derivatives. So let's pull up what function we're talking about here from the previous page. I hope it's not that one. No, it was h of xy. This one here. So the x partial derivative was minus x squared over all this stuff. Let's try to get that in here. So hx means the x partial derivative. It was minus x squared over 4 square root of 1 minus whatever this thing was. This is a function, and I can take either an x partial derivative or a y partial derivative of this function. Ugh. Okay, so the x partial derivative of the x partial derivative is, well, let's do the derivative of this. I actually kind of regret writing all this down. Let's rewrite it again as 4h. As long as we remember that h is not a constant, we'll be able to use this to just reduce the amount of writing we're doing. So the derivative of minus x squared over 4h, we'll use the quotient rule. It's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. We use the derivative that we're using. So like we're doing an x partial derivative. So when I got to the derivative, I had to do the x partial derivative. That's all divided by the denominator squared. What a disaster. Is there anything that I copied down wrong? If not, we'll just see how it goes. So minus x squared over 4h of xy. Okay. Like the question's asking me what sign are these always? And I've got a negative term and a positive term here. So I'm a little concerned. Because I don't see how anything good is going to happen. But let's see how it goes. So I have minus 8 xh plus 4x squared times partial h partial x, which I've already done. All divided by 16h squared. H is always positive, which is nice. I'm not sure we're going to get any good information here. So I'm going to have minus 8xh minus x to the 4th over h, all divided by 16h squared. And the best I can do to simplify this is to multiply through by h, I guess. Like multiply the numerator and denominator by h. So h is always positive, so the denominator is positive. X to the 4th is always positive. X is not always positive, though. I don't see it. I don't see anything good to say here. Well, one nice thing about doing this as a video and being able to edit it is that you don't have to watch me struggle to try to find my error. Here's my error. I found it. The derivative of the inside function here is not minus 1/2 x squared. In fact, the derivative of this inside function is minus 1/2 x. So this partial h partial x should not have an x squared on top. That does not change anything about what we did on the previous page, but if you were watching that and you were like, wait, no, what are you doing? Help, stop. That was my mistake. That's fine. You make mistakes sometimes. It's just when you get further along in the problem, you need to be able to recognize when, like, uh-oh, something's not working out. The way that I was able to figure it out is that the question asked me, what sign is this? Like, is it positive or negative? And I didn't have enough information. So I had to go back, found the mistake. Now we'll fix it everywhere. So partial h partial x actually did not have an x squared. So let's get rid of it here and here. Now when we do the quotient rule, I'll have 4h times the derivative of the numerator. That's 4h times minus 1, plus the numerator, so it's minus x, so I get plus x times 4 partial h partial x. Okay, so what do I have here? I'm going to have minus 4h as the first term. Let's get rid of all this. Except it looks like the h squared in the denominator is all good. So I have minus 4h, and then instead of 4x squared, I have 4x, and this one is also minus x. So in the end, I've got minus 4h minus 4x squared over 4h. I can again clear all the h's by multiplying the numerator and denominator by h, and I get minus 4h squared minus x squared all over 16h squared. Now every variable is squared, so everything that appears, all the terms are positive. So the denominator is positive, the numerator has a bunch of positive terms with minus signs in front of them, so this is negative. So what does this mean? What this means is you take the x partial derivative, which is the slope of this ellipsoid when you're walking in the x direction, and you take the x partial derivative of the x partial derivative. Now we're looking at the concavity of the curve. Instead of the slope in the x direction, it's the curvature, the concavity in the x direction. Luckily, we were able to see that concavity on the graph. This says, like, not only when we walked in the x direction were we at the top, that was the first partial derivative equals 0, also the second partial derivative is always negative, which means whenever you're walking in the x direction, you're always walking on a concave down path. It looks like the same thing is going to happen in the y direction, but the arithmetic will have to come out a little bit differently because there's 25s instead of 4s. Just for the sake of space and time, we're not going to do it. If you take the second y partial derivative of this function, the same kinds of things will happen where you deal with the h's and you'll save some effort by writing h instead of repeatedly copying down everything, like every little piece. But this second derivative with respect to y, I'm just going to skip it for now. Okay, so what do we do with the notation? Well, the purpose of the notation of the little subscripts, where like fx is the x partial derivative of f, is that it allows us to do multiple derivatives easier. So fxx means the x partial derivative of the x partial derivative of f. So that's the x partial derivative of, so we handled this x. Then this x is the x partial derivative. And then the innermost thing was this f, and that's f. If you combine it all together, then you can write it as partial squared, partial x squared of f. This is the second x partial derivative of the function. Notice that we work on it from, like, you shouldn't try to say that you work on it from left to right or right to left, because if you do things left to right or right to left, then like sometimes it'll be left to right and sometimes it'll be right to left. The rule that actually always works is you go from the outside to the inside. So the way I've written it here in the middle with all the colors, what I mean by from the outside to the inside is that this x that's the furthest away from f is this derivative that's the furthest away from f. So the things that are closest to f versus the things that are farthest from f is the right way to compare the different derivatives. You shouldn't try to say, oh, well, in this notation, the one on the right is on the outside, and in this notation, the one on the left is on the outside. Now, just think of it as like outside and inside, and the things closer to the function are the ones more on the inside of the evaluation. So this one, fyy, well, the one furthest away from f in this notation will also be the one furthest away from f in this notation. The one furthest away from f, or the one close to f in this notation is also the one close to f in this notation. And the f is sitting in here. If you combine all this together, you can see that it can be written like you literally just read across. You get, there's two partials, and then an f, and then there's two copies of partial y. So this is three ways to write the same thing, and here's three ways to write the same thing. These are two different second derivatives. Now, the issue is you could do other combinations of second derivatives. Here we've got a y that's really far away from f, so that one's going to go here. And then there's an x that's closer to f, so I'll get that one closer to the f. And then there's an f. So which one do you do first? Well, I guess if you were evaluating this, you would take the x partial derivative first, and then you'd take the y partial derivative of the result. But the main thing is whatever operator is closer to the f, you do that one first. When you read all this, there's two partials in the numerator and an f. And then when I read it in this order, it says partial y, partial x. Here, if you had to evaluate this object, you would say that the partial x is closer to f, so you'd do the x partial derivative first, and the y partial derivative is like on the outside of that. Similarly, this one, I'm not going to do the color coding again. The x is the furthest away. The y is closer in, which is like, we'll evaluate it first, basically. I have too many parentheses there. Yeah. So if you read this across, you get partial squared f, partial x, partial y. So depending on the order that someone writes these letters, they're telling you the order that the derivative should be evaluated. Okay, so this example tells us to find the two mixed partial derivatives for this function. Just to save a little bit of time, I'm going to deal with a function that's a little bit less ridiculous than this one. So let's do the same question, but for f of xy is x cubed y squared minus sine of x squared. So we'll deal with this function instead. Now the two mixed partial derivatives say, well, let's find the derivative with respect to x and the derivative with respect to y in the two different orders. Those are the two mixed partial derivatives. Instead of doing x and then x again, or y and then y again, it's mixed if you do one of each. So let's find fxy to start. fxy, since the x is closer to the f, we're going to find the x partial derivative first and do the y partial derivative of that. Okay, I'm going to keep the y partial derivative for later. Let's do the x partial derivative of this function. So the x partial derivative of x cubed y squared is 3x squared y squared. And the x partial derivative of sine of x squared is, well, we'll do the derivative of the outside function, and then chain rule, multiply by the derivative of the inside. Now we do the y partial derivative of the result. Okay, the y partial derivative of this is, well, we've got a constant and then times the derivative of y squared. So we'll have 3x squared times 2y. And then the y partial derivative of all this is 0 because it has no y's in it. This does not depend on y at all. So the final answer for fxy is 6x squared y. Now let's do it in the other order. So we'll do the x partial derivative after, but we'll do the y partial derivative first. It's closer to the function. Let's put off partial partial x for a little while. Do partial partial y first. Here I'll get 2x cubed y from the first term. Remember, we're taking the derivative of f. And then for the second term, well, this has no y's in it, so its y partial derivative is 0. Then we can take the x partial derivative of this thing. 2 and y are constants. The derivative of x cubed is 3x squared. So this simplifies to 6x squared y. Now you might ask, okay, do the mixed partial derivatives just always equal each other? Like, can we just do whatever order we want? And the answer is, yeah, kind of. Like, you can usually do that if everything is nice. That's a theorem. If both mixed partials are continuous, so if nothing goes crazy wrong when you take the derivatives in the two orders, on an entire open disk, so on a region, like it's, so you can't be like right on the cusp of a disaster. You have to be like, the surface maybe has some messes somewhere, it has some discontinuities, or it has some like sharp points somewhere. You have to be away from those problems by a definite distance. If that happens, then your mixed partial derivatives are equal to each other. Cool. Okay, let's get one more example and then this section is done. So this says, let's get this function of 3 variables. Okay, we've got 3 inputs. Instead of just having the input being x, y, and the output being a height, this is, the input is m, n, and theta, and the output is some number. So, okay, that's fine. Let's look at the theta partial derivative of this function. That's what t sub theta means. So t theta is the derivative with respect to theta of t. So we can take that derivative. M and n are constants. And the derivative of sine theta is cosine theta. So t sub theta is mn cosine theta. Now the question asks, when does t theta equal 0? Well, that happens when mn cosine theta equals 0. How could mn cosine theta equal 0? Well, this is 3 things multiplied together, all equaling 0. So one of them has to be 0. Either m is 0, n is 0, or cosine theta is 0. Cosine theta equals 0, we can figure out a little bit more. There's lots of angles where cosine theta is 0, but it looks like we're looking only between 0 and pi. So the angle where cosine theta equals 0 is pi over 2. While I'm looking up here, it also says that m and n are positive, so these can't happen. So the final answer here is that theta equals pi over 2. Okay, solve the equation then equals 0. So what we found is like that the theta partial derivative of t equals 0. That means that, like, why would we ever take derivatives and set them equal to 0? Like, what was the reason to ever do that? The reason you take derivatives and set them equal to 0 is it doesn't matter what the application is, physics, biology, economics, anything. You take a derivative and set it equal to 0 because you're on the hunt for maximums or minimums. This angle, theta equals pi over 2, seems to be, like this is our candidate for there being a maximum or a minimum of this function. To figure out if it's a maximum or a minimum, the easiest way probably is to look at the second derivative. This was called the second derivative test. The second derivative test is the idea that here's two different points that have a first derivative equal to 0. If the second derivative is negative, then this is a maximum. And if the second derivative is positive, then this is a minimum. Like a concave down flat point is a maximum, and a concave up flat point is a minimum. So here we can find t theta theta, which is another theta derivative of mn cosine theta. We get this. So t theta theta of mn pi over 2, like at our critical point, is mn times minus 1, and that's less than 0. So we've got the first derivative is 0, the second derivative is negative, so that means that theta equals pi over 2 is a maximum for this function t. This function turns out to be, like this is how you find how much torque there is if you push at a certain angle, and it turns out that you get the most torque if you push perpendicular to the axis. If you, like, I can't assume that anybody knows any specific amount of physics, but like, I don't know, if you're ever holding a wrench, you should pull perpendicular to the wrench to get the most torque. Okay, so what did we do in this section? We took partial derivatives. To take a partial derivative with respect to a variable, you declare that all the other variables are constants, and you take the derivative in that way. This had some geometric meaning. It represented the slope of a surface when you walk in different directions. So I had my cylinder here, and from some perspectives, this point was flat. Like from the x partial derivative was 0. It meant this was a flat point. The y partial derivative was positive. It meant that it sloped. Depending on which direction you're going, you'll get different partial derivatives. So that's what partial derivatives are for geometrically. Then we dealt with the second derivative and some mixed partial derivatives to try to figure out what those were all about. Got to see some pictures of it too. Do some homework, do some practice problems. Partial derivatives aren't going anywhere.